Hi everyone, welcome to this event. My name is Matteo. I am the head of the tutorial team for the conferences in Develer. I'd like to remind you that if you like this, the event of this year, you may like to thank us, me, Fabio, Mirko, Daniele, and Federico. While if you didn't like them, it's my fault. If you are interested in knowing what we are preparing for the next year, subscribe to the newsletter by clicking above. Today, I am here as a moderator and presenter instead of Laura and Latara to welcome you to this GoLab event, Baker, a story about building big data pipelines in Go. First, I'd like to introduce the guests for this evening. So the first guest is Valentino Volonghi, also known as Dalton. We met many years ago at one of the first Python conferences in Italy, but now you will find him more often in another time zone as CTO of NextRoll. The second guest, because he is also the host, is Giovanni Bajo, also known as Rasky. We met at a job interview, my job interview, a few years ago, and now he is the CTO of Develer. While you may already know something about Develer, that, for example, we try to be the optimal development partner for a wide range of clients, you may ask who is NextRoll and what they do. So I am going to leave the first question to Valentino to introduce the audience, something about NextRoll, and something about the data streams that led to the creation of Baker.
Hey, thank you, Matteo, and thanks GoLab for having us here to have this nice conversation. NextRoll is, well, as Matteo said, I'm the CTO of NextRoll and also co-founder of the company. We started the company in 2006 with the intent of helping small, medium businesses of any kind, of any vertical, to display and manage their marketing online. And to this day, this is still the mission. Effectively, it has grown in size. We now have tens of thousands of customers, over 30,000 customers. We have two business units. The one that works with retail companies that sell products to retail, and a business unit that works with companies that sell their products to other companies, called AdRoll and Rollworks. And effectively, our product portfolio goes from online advertising, which I'm sure everybody is aware of, with all of the privacy implications and evolutions from legislations around the world, to email marketing and just marketing on the website directly, and analytics and attribution, which is a particular kind of feature that allows customers to determine the causality relationship with the marketing campaigns and the results that they achieve with those. In order to do all of this, you can imagine there is a lot of data is generated. One particular aspect around data generated is advertising today is traded in real time globally. And I mean it in the strict sense of the word real time. We receive about 150 billion requests per day. That's a peak of 4 or 5 million requests per second, and globally. And each one of these requests individually must be replied to within 100 milliseconds. So we have 100 milliseconds for processing, understanding the request that we received, typically from the likes of Google, for example. And we have to then query a machine learning model for the price that we're willing to pay for this particular ad, or if we're planning to send an email, of which we send many hundreds of millions, we have to determine what's the best content to put inside this email for this potential customer of ours to achieve the results that they're aiming for. And yeah, in order to do this, we receive the data coming from our customers, and this is where the relationship with Giovanni, professionally speaking, really started to take for a turn for the better, and we started to work on Baker many years ago. I think at this point, maybe it was 6 years ago, something like
something
that.
like that. Something like that.
Yeah, we were 6 years ago. So in general, we ingest on a daily basis. We ingest something along the lines of 400 terabytes of data are ingested. Many of those come through the exchanges, but all of this data needs to be processed effectively as a stream in real time, because we need to replicate all of that data globally after we receive it, because and process it, because the speed of light has certain limitations, and those 100 milliseconds that we need to respond within, they're fixed. And so 6 years ago, I think you, Giovanni, came to the US, right? We were sort of working together already.
Yeah, because we first met actually during the PyCon Italia conference. We actually co-founders of the PyCon Italia Association. And we met in 2006, maybe 2005 or 6, and we started making this conference together with, of course, other people. And so we were in contact, professionally speaking, for this conference for a long time, but we haven't had the chance to work together on some projects. And then at some point, Valentino called us and tell us he was looking into a contractor to do some job and was looking into Develer. So we started working remotely for them. They are based in San Francisco. We are in Italy, of course. So there is also some time zone challenges to fight. But anyway, so I think we had just started. Maybe we were working for a few months. I don't remember exactly the details. So at some point we decided to flew the whole team to San Francisco to actually, meet in person with other colleagues there. And I went with the team there, and I stayed for a week. Took a chance to also meet the founders of NextRoll and the board in general to see how Develer could fit into their company better. And back at that time, I think the point was that you, Valentino, invited me to like a post-mortem meeting that just happened in that week. It was a post-mortem about some big data infrastructure, right?
Yeah, we were using this Java application called Apache Storm, that I think is still around. I think now it's version 2. It was originated from Twitter. Created this framework for real-time stream processing, and together with it, they worked on the Lambda. They were some of the first people talking about Lambda architecture. So having the ability to run the same code on a stream and in batch mode. And the first version of Storm that we were using back then just had a lot of stability problems, and it failed frequently. Couldn't handle the load. We were deployed in Amazon AWS. This was a lot of instances, and the core of the work that this was doing was effectively receiving CSV lines coming from these real-time streams from Amazon Kinesis, and it was supposed to parse these lines, validate them as best as it could, gather some fields from the CSV, and then re-upload this data back into DynamoDB around the world. So for a single line that would come in, it may have needed to do 4 or 5 writes to DynamoDB, depending on the region. And I just couldn't. I've been a software developer for over 20 years at this point. It's sometimes you just take a step back when you deal with these infrastructures, and you're like, how can this operation, it's so trivial, You're just receiving CSV lines on one side and writing them on another side. It's a single step. How can this be giving us so many issues? It wasn't even the first time we had a postmortem of that kind. And for a long time, I was asking the team to rewrite it or figure out how we could avoid problems. The team kept telling me it's not a library. We just need to use it a little bit better or something like that. And after a few years, my patience ran really thin. And while you were in San Francisco, I think we started talking about Go or Rust. I was undecided between the two, and I think you convinced me to go with Rust. Sorry, you convinced me to go with Go at the time.
Yeah, that's because back at the time I didn't know Rust. I had never tried back at the time to write some Rust code. So while I was already familiar with Go, I had already written, I don't know, maybe 50,000 lines of Go. So I had let's say, decent understanding of the performance trade-offs. But I think that the thing that motivated me was that what you just said, right? That the problem is actually trivial because you are getting one CSV line, you are just parsing a few of those fields to make sure that those lines are validated, basically. So, of course, we are oversimplifying. The real world is always hairy. But if you think at infrastructure, it's really easy. You get these lines, you just validate them and push them into another API. So it really cannot be like a complicated problem. So when you basically deep down from using like a very huge framework that try to maybe solve a lot of complex problems like distributing load across many different servers and so on, and you just switch down to the basic low-level mentality where let me just really read one line with the syscall read line from the kernel, let me just parse those CSV one byte at a time and let me push them back doing one single HTTP call. You find out that this always pays off from an optimization standpoint. I'm really kind of an optimization nerd, and I like to really squeeze systems to the best performance possible. And most of the time, this involves basically removing layers of abstractions and frameworks and so on, and getting back to the actual problem, writing down at the syscall level, so to speak. So this motivated me. And also back at the time, I think you were preparing to open source the TrailDB database. Which is actually is the same philosophy. It was written in C and was a way to do complex stuff on a single computer, not spreading across different servers, but say, okay, if you write a code which is efficient enough in C on a single computer, you can probably substitute a framework of many different servers, and the system will be more stable and probably fast enough to do whatever it takes. So basically, it was the same approach that I started thinking, why we cannot do this for the CSV parsing problem, basically.
Yeah, and you said. I think you said I think Go can handle that. I think that was it that you mentioned this to me. Like I think a single server in Go can probably deal with this. And I said, "Are you sure this is going to be something like 200,000, 500,000 scale lines per second that needs to be processed?" And we're like, "Yeah, maybe it can do it. Maybe it's going to be two servers, but it's going to maybe do it." And at the time, I thought I agree with you probably, but how do I get this done through the team? As a CTO, it's one of the challenges is at least the type of CTO I aspire to be is not one that rules by terror and it's kind of like dropping the law on the engineers. I like to leave a lot of autonomy. So it always is a big conversation, especially when the team is invested in Java and this new software would be in Go. They would ask a lot of questions. So all of their skill set would start from scratch in a way. I think I disagree, but some engineers have this mindset, and so at the moment I wasn't sure. So I think kind of like in secret from the team, I started working on my own time on this.
Yeah, I remember you telling me, please make sure don't tell your team because I don't want the word to spread around the company.
Yeah, I just wanted to first check it was even possible and how complicated it was going to be. And I started writing early on, and I was doing this alone at the very beginning, and I think I spent a week trying to figure it out myself. I wanted to there was already some going in the at NextRoll already, so I wasn't too afraid of introducing something new. And I started playing with it. I started looking at the basic stuff, reading from Kinesis and writing into S3. Except that rather than reading from Kinesis, I started doing this by reading from S3. Just download a file from S3 and parse it and write inside DynamoDB. And at the beginning, it was very simple code. And I remember reaching out to Giovanni and saying, wow, this code is really fast. It can do this thing that I just put together in a second, can do from disk. It can do 100,000 writes per second into DynamoDB. I'm very impressed. And Giovanni started asking me, oh, that's cool. Yeah, can you show me the code? And so I shared the GitHub repo with him. That I think was both a great decision as well as very humbling, I would say. Because Giovanni, as he said, he's a pretty optimization nerd. So he went really deep into the into the code very quickly.
Yeah, and I started working out, and then of course I was also more familiar with Go already, so I knew, like for instance, I don't know, the CSV parser back at the time was doing one memory allocation per each line. I think they fixed it a few, I don't know, years ago or something, but back at the time it was like that, so I knew that was not going to work. So because, I mean, the main thing that slows down Go in general is memory allocation, because it's a managed language. So memory allocation is probably where you usually need to fight to make sure that your code is fast. So for instance, changing the CSV parser from using a standard library to doing some manual parsing code that does no allocation whatsoever, no memory copies. So for instance, instead of, you have a big string, instead of splitting this big CSV line into one string per field, if you have like 500 fields, there will be 500 allocations. You just, keep references within the original string of where each field is located, and then you can use them without allocating, directly accessing the original data in the CSV line. Stuff like this are really, let's say, low-level trick to make sure that you don't allocate, and then the speed can go up a lot at that point. And we quickly reached actually the target on a single server. So we had like a toy, because it was a toy back at the time, a toy project that could push CSV lines into DynamoDB at the target speed, and it was probably faster than the Storm architecture with multiple servers, basically.
Yeah, no, the Storm architecture was only able to deal with 20,000 lines per second per node.
Yeah. And so basically that, of course, validated the project, because it meant that you could really do it in Go, and it was fast enough to do on the single server. And when you do it on a single server, you mean that you have a very, very, very few problems to handle in, handling multi-server communication and synchronization and so on. It's everything gets very easy, and basically. So we started from there, and the idea was to build this kind of, let's say, composable pipeline, so that you can basically have different components, where one is the input component that basically feeds CSV line into the pipeline, and you can configure it, can get from S3 or, whatever source, different sources, Kinesis or whatever you want. And then you have a pipeline made of different filters that you can use to process and transform these lines. And then at the end, you probably want to push them into a PostgreSDB, TrailDB, or DynamoDB, or a different kind of, or S3, or a different kind of storage. And so we basically came up with this architecture where you have like a single TOML file that you can use to configure where you're getting the data from, the different filters you're using, and where you're pushing the data out. And then you run Baker basically with this TOML file, and it will do the processing for you. And it's completely stateless. That is another important architecture decision, because it means that you don't have any states to manage. You just run it and will process it, and then there is some checkpoint system to make sure to continue, or not to waste, to restart from scratch at least. But the architecture is completely stateless, and this also helps a lot.
Yeah, we took it off. This often happens actually, and we hinted about this at the start, right? Where sometimes you have these big frameworks, they help you do 1,000 different things, but in order to do that, they take all of the trade-offs that are needed to execute the framework with a particular, API and idiomatic code that they're planning to build. But if you're looking to solve a very simple problem like the CSV file, a lot of those trade-offs may not make sense to you. It may not make sense to slow down everything that you do, because you're looking to, for example, support multiple different types of lines coming through. And like parsing JSON is a thing that this framework still doesn't support really well, because JSON parsing is quite complicated in reality when it comes to managing allocations and all of that. Whereas CSVs, they are a little bit more awkward, because you always need to read them all in memory if you want to do something with the CSV. It's not like a nice binary format that you can just seek down to the field and just read the field. The CSV, you just need, there's no prefixed size of the line or any of that. So it's a little awkward in a lot of those. But if you're dealing with streams pass from memory anyway. And so a lot of the trade-offs that you need to deal with in other occasions, you don't actually need to deal with those in this case, and you end up with performance that it's really ridiculous. In this case, in particular, we were playing around with. I was playing around during a reInvent 3 or 4 years ago, and I remember deploying this on a CE3 8XL. Those were some of the bigger instances out there, and effectively, there were two bottlenecks at the time when running this. One was the gzip decompression, which can only run about 140 megabytes per second per node per CPU core. That's the maximum speed it can deal with. And the second bottleneck, instead, if you weren't to do gzip, was network. So you basically would have the CPU sitting idle because waiting for the network, or you'd have the CPU busy decoding the gzip stream and the network doing nothing, which was actually one of the motivating reasons why we decided to effectively move all of our compression to Z standard, which is much stronger compression than gzip. It's about 2x. And on the average case is about 2x better than gzip, but it's 10 times faster at decoding. So you get 1.2 gigabytes per core, per CPU. And you get rid of both of those bottlenecks. You end up with now the CPU is back to being the bottleneck. And in those situations, Baker is able to push a million records per second, process a million lines per second off of a single box. It's something that's always very surprising, but we made a lot of decisions, a lot of trade-offs through, for example, the statelessness. One of the big things in Apache Storm is that they have this group by functionality embedded in the framework. But group by means that I need to have a map of all of the keys that I'm managing. I need to associate the key to each line that I'm managing. I need to have a map of who's managing the key currently so that I can route. Some of the bandwidth is going to be wasted in internode communication and keeping the map up to date. This is a ton of work. And when we looked at the topologies that we were dealing with, almost the totality of the topologies that we had were effectively single node. Like everything could have run off a single node. It was a single step. And if you run everything off of a single node, a lot of the use cases that you may need the group by for kind of go out the window, because you can just group by of the same node. You don't need to distribute this around. Likewise, another big one is flow control. When you're managing a stream in real time, you want to make sure that whatever resources are downstream, if they become slower, that you don't have memory buildup in the cluster. This was the original reason for why we were having a failure with Storm, was effectively the downstream systems were becoming slower. Downstream from Storm were becoming slower. Storm was building up a queue of writes to DynamoDB or other systems, and eventually would run out of memory and crash. And it kept happening over and over again. And my team was telling me it's because we don't use the acknowledgement system properly in Storm. We are doing this flow management wrong. And when talking with Giovanni, he mentioned channels. Go channels are perfect for doing this. And we worked together and on this one as well. And we started creating, the channels in Go that had a known size, a known queue length, and they manage your backlog for you. And the architecture that Giovanni came up with with the topology input and output, how it was written, made it so that this just happened transparently. Once you chose the sizes of the channels, if the downstream writes became slower, then the system would read slower immediately. So the system effectively, once at volume, it never changes how much memory it uses. It's always about the lines that are on flight, the average processing of each line times how many cores, workers, and whatever you deployed, and that's it. Stable. It was an incredible relief to be able to see something like that getting off to speed so easily.
Yeah, like a pipeline of channels in Go, you can basically make sure that from the input you feel the back pressure coming from the output if the output is too slow, which means that you don't need to have a way not to buffer indefinitely, but it's by itself. It makes sure that if the output is low, everything will get full. Every channel in the pipeline will get full back to some point where the input will block because the first channel is full, and then automatically the system will just, let's say, pause, slow down, so that to cope with the reduced speed of the output, without allocating too much, without wasting too much memory or going into OM, which is important for this kind of software. And so I think this worked out very well, very quickly. We managed to deploy or to at least test it immediately on one of the first pipelines, and it was working okay. And then, of course, over the months, we build additional filters to make sure that Baker could be used for different pipelines, for different use cases. And then the project grew a little bit at a time in NextRoll.
Yeah, I think. As I mentioned, I don't like to push things up from the top, but in this case, I had built something on the side that was significantly faster and more critically, more stable and easier to operate than anything else that we had built before that. Me and Giovanni had, of course, written this. And not only that, but as I mentioned, this was initially thought of for managing streams, but in practice, if you streams from Kinesis, but in practice, we ended up developing it for files from S3, and files from S3 are more like files from a file system. So we ended up, one of the things we did was also extend this new system to be able to also process files in a batch fashion effectively, so that it could read files from S3, parse them, process them, re-output a log line on the other end, or a different format of a log line to a file and then upload back this file to S3 for processing by another stage. And other people in the company at that point, they were looking for a system that was capable of processing large amounts of data, talking about petabytes at this point, and do this across a ton of instances and reliably. And in particular, this is the critical aspect on the spot market. So on AWS has this class of instances called spot instances, where rather than paying a fixed price and they remain with you forever until you turn them off, when you work in the spot market in AWS, you effectively, at the time, you would run an auction. You would bid, say, 10% of the price of the instance on demand. And if at any point in time after the first hour you ended up not having enough money for that bid, that your bid was too low, then they would take the instance away from you. So there could be termination of the instance at any point in time. So it was critical that there wasn't state around when dealing with this, that you could restart the instance and redistribute the job to it quickly, and that the instance were fast, because the shortest time the job runs, the less chances are that you'll be interrupted. If it takes less than an hour, you won't be interrupted for the full hour. And so you're just paying 10% of the cost that you would otherwise. And other people in the team realized that this was a great way to save on cost when processing petabytes. And they started building a framework around Baker that effectively did allow them to process petabytes of data each individual day. And even there, they came up with interesting ways to do the coordination step. Rather than doing it by having instances communicate with one another, again, due to the overhead of things like group bys or the reduce step of a map reduce function, they decided to create a hash function, which we implemented in Baker as well, to basically create a sharded output that was sharded equally across the same keys across all instances. And then the files would be, these shards by instance would be uploaded to S3, and then a secondary job running after this initial Baker job would grab all of those files and from each shard and join all the files from the same shards, effectively recreating the same thing that a MapReduce framework was, but without any state management living within the code that we have built, instead leaving the state management to storage like S3. And this became very, very convenient at the same time, because right around this time, S3 started growing the ability to have individual streams be able to go at 5 gigabits per second. Today, you can read from S3 up to 100 gigabits per second from even the same instance. And if you think about it, the SATA 3 interface can only do 3 gigabits per second. That was the interface that was more popular on S3 at the time. So effectively, reading from S3 ended up being throughput-wise faster than reading from local file system. And so effectively, the framework that we ended up building was pound per pound as efficient in terms of throughput as any MapReduce framework with a file system and local data living in the same local machine. And the framework from that started growing and growing. Other teams started to adopt it, from machine learning jobs to analytics to processing streams live in real time globally. And because Go is a simple language, because at the end of the day, that was another good choice that we made at the time. Go is a really simple language. People that are familiar with Python can pick up Go really in like a couple of days. Other people started to contribute in filters. Other people started to adopt and modify Baker for their own use cases. And it grew quite a lot in adoption, to the point that I didn't have enough time to manage that process, the project anymore. And I still needed to write unit tests. That was a bad thing that we didn't do so much of at the time.
And so, but the choice of Go, I think it was correct under many different points that we discussed about. There are also a few things where Go was not the best choice, of course. So I would like also to discuss about this because it makes sense to balance out benefit pros and cons. And one of the problem we had is that the Go compiler is not on par with let's say GCC or LLVM. So when you have like let's say very CPU intensive kind of processing like algorithmics, compression algorithm, for instance, usually with pure Go code, you don't get at the same speed that you can get with C or Rust or another, let's say, another language with a more advanced compiler. So basically, for instance, for gzip, I remember back at the time, there was a gzip implementation in the Go standard library, of course, but back at the time the compression speed was about twice as slow than the C implementation of gzip that you find on your command line. So basically, what we ended up doing to quickly fix this was to basically spawn gzip externally as an external process and pipe data through it back into the Go process to recover that missing speed, for instance. Of course, there are other solutions like I'm sure now there are many CGO wrappers that allows you to import a C implementation of gzip into Go, or I'm sure also that the Go implementation itself is evolved and the compiler itself is evolved. So maybe the difference is not 2x anymore. But for instance, this was a compromise we had to take at the time. Another problem we had with Go is that Go, it's very cool for the static binary stuff where you just compile one binary and just copy it to the server and run it. That is one of the most known selling point, but it doesn't allow to do plugins, for instance. So you cannot, have like runtime loaded libraries, like plugins that you can load a runtime, compile separately and load them, which would fit perfectly for Baker because Baker is a pipeline of filters that you basically define from a configuration file. And so it would make sense that each of the filter is a different plugin to Baker that can be compiled independently from Baker itself. But Go doesn't simply allow that to be done. So we internally in NextRoll, so what we did is basically there was one big Baker repo, and all the filters from all the team was being committed into the main Baker repo, and they were part of the Baker binary, official Baker binary. And then for the open source release, we switched to a different model where basically Baker can be used as a library, so that yes, as a framework mainly. So basically, you can write your own filters and register them into the Baker core and then run Baker. Just as a way to work around the plugin system. I think in another language, the solution would be easier. We'll just provide a small SDK to write filters, basically.
Yeah. Also, you mentioned earlier the garbage collector,
Mm-hmm.
how much work we do in Baker to make sure that nothing is ever allocated unless it's absolutely necessary.
Mm-hmm.
And there are other frameworks out there that are similar to what Baker does. But for example, because they chose to parse more type of lines, they end up allocating a lot more. And it just doesn't work for us effectively. We had one speed really is critical. And for example, one thing we did recently is optimize the reserialization of a line coming through Baker. In case you may make updates, for example, one decision we made back then is never modify the line coming through. We allocate a fixed array, a fixed slice of say 256 long slice that we just use to store whatever edit you may want to make on the original line. when you go to reserialize, you have to merge these edits with the original line. And we made some, we had some code around it that was relying on a bug in this system at NextRoll, and this got patched over the past year. And when the code that was relying on it was updated, they discovered this code is 10 times slower now. And that was not fine. So we had to go back in and optimize the line serialization and made it back to 10 times faster. So it was slower because it was allocating a field twice effective. That was 10 times slower, the final result. So all of this stuff is if you get used to running that fast, it kind of it makes a lot of things really, really hard. not allocating in particular. Yeah.
I think you answered most of the questions I had. I think I have a few one. You may ask a few questions now, and if you'd like to continue talking a bit, we may have a pause you in a few minutes. So the first is, what is still unsolved in the current code?
You mean on the open source
that is pending? And the other question is, why releasing the Baker as an open source project? So what do you expect from it?
Yeah, well, I think as we mentioned earlier, I think unsolved. We would love to have more types of lines supported, and including maybe JSON. We just need to come up with the right way of parsing it that doesn't allocate effectively. And another aspect that would be nice is more unit testing for the entirety of this system. Because it was developed a bit more of an experiment. I did not really think that it was gonna become much bigger project lasting so long. There's not a ton of unit tests except for some core pieces of functionality, and more on the filters side rather than on the core. Yeah.
And for the open source question, I think that we discussed from the get-go that if this could work, would be a nice open source release. I think NextRoll has been releasing open source software over the years. As I mentioned before, when I was there, they were discussing about releasing TrailDB as an open source, and I was following that team. And the TrailDB database in general is really, I think, a nice piece of code. And so I think the plan was to get Go to release it. It took a while because when we decided to actually went through with the open source release, of course, as I mentioned, there was this, let's say, Baker monorepo where everything was inside, and of course much of it was let's say NextRoll specific data and NextRoll specific filters. So you had to come up with a way of removing everything and have a cleaner architecture where there is some standard stuff that you can open source and general use, and then separate the NextRoll stuff into different filters or customization, so to speak. So it took a while to migrate from the first repo to the new open source repo. It took several refactorings, but then eventually was released, and it's now on GitHub for everybody to play with it. There is a lot of documentation too. I think it's a cool open source piece of software that you can start using right away, and it can solve already a lot of problems.
Okay, I think we can, if you are interested in the chat, you can see the links of the main website of Baker or the GitHub pages. And we can have a short break, a 5-minute break to let anyone get up and drink something. We will later open the question slot. So if someone in the audience has something to ask, think about it, and we will open a special chat for it. Don't use the main one because we will lose the questions inside there. So we can see you later in 5 minutes, and we'll be back at 18, or I don't know your time zone, in 5 minutes. Goodbye. See you later. Okay, welcome back. Later on, we will start a QA session. So when you see it appears, write there your question if you have any. Going down, I think you answered a lot of my doubts about Baker. So mainly, there was one time a complicated system with multiple server that was ingesting some data at very high frequency, and you ended up writing it as a single process that runs on a single machine that does better the same work. So maybe you haven't had a reason to explore how to scale it even more. You run it on a bigger machine.
Partly, I think at the same time, we take advantage of some of the functionality already provided by Amazon. Or we build some things to help us scale. So in all the cases in which this is a stateless service, it's just adding more machines. Each of them processes its own shard or set of files. And then once they're processed, typically the first step is managing the most data. Then the second step, the reduced step, is dealing with an order of magnitude less. And another alternative here is in terms of stream processing, a single box is usually not enough to manage Kinesis streams. You need multiple boxes. And one of the additions that working with the team, also from Develer, we did in the past year was to update the library for integrating Baker with Kinesis, adding the ability for the various nodes to coordinate, but without sending data to one another. They just talk with DynamoDB, and they assign each other shards that are available from Kinesis, and then they manage themselves autonomously. So if you add more instances, they know how to spread that load. We actually have a tech blog that we wrote on the NextRoll tech blog with the folks from Develer that talks in depth about this topic. I can maybe share a link to that.
Thank you. Or in the chat here, or on Discord later. Thank you very much.
Yeah,
and another thing you perhaps briefly answered about it. I know that I have heard that NextRoll is a shop with a lot of languages inside. I think you use Erlang for something. You have something in, I think, every language on earth, maybe. I don't know if it's exaggerated, but why Go at the end if you can choose between a very lot of other languages?
Yeah, I think Go hits the sweet spot in a number of ways. It has its batteries included, like Python. A lot of the standard library in Go is extremely high quality, and it's effectively very fast for a lot of its pieces. And so people don't need to put in too many dependencies, and code will run really fast. I rewrote after getting a little bit more familiar with Go, thanks also to Baker. I rewrote an internal component that originally was written in Python to do authentication and authorization. And the only thing it does is it receives HTTP requests, queries a database, and responds okay or not okay effectively. Again, it's one of those things that you're like, with a little bit of experience, just take a step back and you realize, okay, this thing should be doing tens of thousands of requests per second on a box, and they should all be single millisecond latency, because this is the complexity of this job. And if it takes longer, then there's a margin for improvement. And the Python component that used to do this was had basically a tail latency of multiple seconds and an average latency of over 200 milliseconds to do this simple thing. And because this was the core authentication service of everything, in some occasions you may query it 3 or 4 times, 5 times or more for a single request from the user. So those latencies start to pile up. I rewrote it in Go. The tail latency went to 5 milliseconds 95% of the time, and 200 milliseconds as max latency, all running from a couple of containers with less than 200 megabytes of memory available to them. So it is that kind of language where if you pay a little bit of attention to what you're doing, you get a ton of speed out of it. Speed that you just cannot possibly get in Python or many other languages. You can get it in Java, but doing the same things that you do in Go in Java takes a lot more code, a lot more knowledge about what the language does underneath. It's not as intuitive as a way of processing things as Go is. For all the things that I may not agree with the original Go language design that did not include generics, for example, they just made a ton of really good decisions. Like a lot of them are really nailed. And it makes the fact that it's intuitive makes it possible for an entire team to pick it up without needing to go through classes or, going crazy on it. Like people go with lifetimes and ownership in Rust that are a much more complex topic than channels and Go routines that people seem to pick up much quicker. So I think for me that's the core reason. It's just much faster, very easy to use, without needing to put a ton of effort into it. And ultimately, if you run a business, this is the thing that matters the most.
Okay, summing it up, the lesson learned as CTO, what you can suggest about all this story? I think you already talked about it, but if something that you may extend and broaden a bit on.
Well, as a CTO, what I learned is throughout this process, is how to roll out a step improvement on the infrastructure. Personally, I think if you have a way to, there are many kinds of CTO in the world. The kind of CTO that I am, that I want to be, is one that remains close to the code and continues to write code occasionally. Of course, I have a lot of other tasks daily, and I cannot spend a good chunk of the year writing code. If I'm lucky, I get maybe a month or two out of the year where I can write code. But what I learned is sometimes there is a way to work with your team, and if you realize something you're doing is incredibly inefficient, and that if you've solved that inefficiency, you could create opportunity for everybody to be more productive, then that's a good place to go as a CTO. And if you can write that code with some experience, you can realize these things don't work the way they are. They could be 10, 100 times faster. Write that code, show how it works with people, show that it's a lot easier. Tens of thousands of lines of Java were replaced by 3,000 lines of Go. At the end of the day, our original version of Baker was 3,000 lines. So it's mind-blowing what you can do. So a lot of times people say that, what is the say? If you wanna Yeah, I forget the saying, but it goes something like, if you want to write something well, you're going to need to remove a lot of code and it takes a longer time. I forget the saying exactly, so I'm butchering it.
I mean, the basic rule of optimization is avoid doing stuff, because that's
Sure.
the faster way for the CPU to do, is not to do stuff. So basically, removing code is a good way for making things go faster. And also, you mentioned some line count, but I think the point is also that if you had to compare not only the line count of the Baker compared to the Java version of the infrastructure, but also if you include in that figure also the line count of all the third-party libraries that the software was built upon, the difference will be even higher.
Yeah.
And that is the reason why it's faster, because it's simpler code, because the task is essentially simple. So you don't need to complicated code to do that. It's just that if you build it on too much abstraction, you can end up being too slow for this task. So this is why we can make it faster, because it's a simpler code with no abstraction layers to go through, that does exactly what is required for the task.
Okay, I think we can open the question. Meanwhile, let's see. Meanwhile, we are opening it. Do you have some idea? Can you tell us the smaller cases or the strange cases you have seen Baker use it in, both inside NextRoll or outside? To maybe not everyone has a multi-terabyte stream of data to manage. So where can Baker be used for normal people, normal smaller scale problems?
Well, I mean, you can technically use it for any use case where you need to download data from a location and do something quick on it and write it back.
Tabular data.
Yeah, tabular data of sorts, or have a one endpoint that I don't know if it's still in the open source version of Baker was that I wrote, was a WebSocket page that would tell you the current state of what's being parsed through a filter. Whatever was written by the filter through the infrastructure would end up in the WebSocket page. So you could use it to just see streams and have it as an endpoint of activity, and you can just see it live. You could, I mean, we have used it for a lot of things. We tend to use it for one-step data pipelines, but because it's a library, you could use it on a command line interface software if you wanted to. For example, I see now that we have 130 something stars on the project on GitHub, but none of these folks have wrote back to us saying if there's something nice that they're doing or for issues about it. So we have 12 forks though.
Okay. Are you interested in filters, or I've seen the code is AWS centered. So are you interested in some other input or output to contribute back or stuff like that?
Yeah, for sure.
Okay.
We would always maintain though that the requirement of being extremely fast, not allocating being stateless, so no state management inside Baker. Those would probably be tenets that we would continue to try to live by. But other than that, definitely open to anything.
Okay. We can ask the question. We can open the question session. Okay. When we are waiting, I was curious because the getting started session of the site states what you said before. If you want to use Baker, you mainly write a main in Go with some import and configure a bit of the plugins. Then you write a TOML file, and that's done. So if you want to make something different, you usually, if you want to use Baker, you have to write something and build it because of the missing plugin feature of Go. Does it work?
I mean, you would have to build the plugin anyway, right? Even if you were writing the plugin, you would write the code, build the plugin, and then write a TOML file and run Baker. So what you do now is basically you write the code of your plugin, and then when you build it, you're also building the Baker core, and then you just run it over the TOML file. So at the end of the day, from a development standpoint, it doesn't change much. Of course, you lose that kind of flexibility where you can use, I don't know, the official Baker binary release 1.5, and you just plug your plugins in, because it's always, let's say, custom binary that you have to build with your own stuff on it. But besides that, I would say that for the development workflow is mostly the same. It doesn't change much.
Okay, we have a first question. Is some kind of observability existing in Baker, for example, export metrics to Grafana or stuff like that?
Yeah, that's a great question. So we have each filter can build its own metrics that can aggregate it at the instance of Baker. And then, yes, Baker supports the ability to send the data via statsd effectively. So we use Datadog as a system internally. So all the metrics are generated by Baker are pushed through Datadog, and then we look at all of the dashboards over there. Since I think statsd is also supported by Grafana, so you could forward those metrics inside Grafana and see your dashboards in there. And similarly for other systems, we haven't done any other but statsd because that's what we need. But it's possible. This one in particular is a very separate component, so it would be very easy to add a very different way of monitoring things if someone had a different one that is not statsd. Like CloudWatch, maybe someone uses CloudWatch that doesn't use statsd, for example.
Cool, that's interesting. And you told before us about back pressure. Do you need something to monitor it, or is something that I think at the end this is a very small component, so data locality or other problem, you are moving outside from the tool. You are managing where the data is, you are sharding outside, and then you are firing Baker on the data where you put them. So there is still something missing inside it, or is something that you are moving outside from Baker, so you don't want adding more inside Baker?
For back pressure?
For back pressure, for other, for example, data locality, I think one of the problems that they have. Of course,
I would data locality really depends on the philosophy of the team using Baker. I think Baker should remain agnostic, keeping it small code-wise, and is at the moment I'm not exactly sure how you would add something like data locality from within Baker without making it significantly more complex. Because right now Baker just knows a very simple flow, and that's it, which helps keeping it extremely simple. So yeah, I would leave the task of dealing with data locality to whoever is implementing Baker. Because in our case, we have no need for it. All of our data is stored inside Amazon S3. So we never have any clusters that are persistent. But if you instead do have data persistent, you can trigger Baker on your cluster via containers, point Baker to the file system that to the directory in each machine that contains the data that is local, and then run it on that box. And if there are other boxes as well, then store the results somewhere that can be reached, and then process the results, maybe still with Baker or maybe with something else if you have something else there. There's another topic here, a corollary of what we've been talking about on using sometimes not using big frameworks, but using small files, is that it may not be optimal to use Java for the entirety of the job. Some tasks may be better in Go, some other tasks may be better in Rust, some tasks may be better in another language. And Docker and platforms like Airflow from Airbnb or Luigi from Spotify create the capability of creating very heterogeneous computation clusters that can run different jobs on different stages of a job in different languages, optimized for the specific task. You don't need to have 1,000 languages, but usually you may have Java and Go and Rust, C, Python, or this kind of pairings. So you choose the right job for each step.
Okay, thank you very much. So I think we are in the era where the cloud and the S3 stuff like that are like files, and Baker is something like grep and cat and the pipeline we used to do in Bash, but on a petabyte scale.
I think once I saw a blog post that was about Bash is your big data processing tool, or something like that. It was kind of a joke blog post, but I immediately thought of Baker while reading it, because I think the basic idea was the same, is that you can basically use simple tools to do this kind of flow processing very efficiently.
Okay, I think that's all. We have no other question. I'd like to thank you very much for being with us and sharing the story of Baker. I think one of the first questions in the chat was, do you plan to do a workshop or something like that on Baker? Sorry, this is not the time for a workshop, but we accept the suggestion and we may do something in the next edition of GoLab, maybe. We will think about it. And I think that's all. If you want to follow us, maybe we will show again the link to the newsletter, or if not, you can find it on Discord. And I think, okay, it's up here. So thank you very much. Thank you, Valentino. Thank you, Giovanni. If you want to hang out a bit later or after dinner on Discord, you are welcome. Maybe someone has something to ask or to share with you. So have a good evening and good night.
Thank you
very much.
Cheers.
Goodbye.
Thank you.